Ready to dive into some seriously cool math.
I'm ready. Let's do it.
Today we're talking about infinite dimensions.
Sounds intense.
It is kind of mind-bending, but also super relevant to everyday things.
Like what?
Well, we're basing this deep dive on a research paper.
Okay.
And get this, it's called Non-Negative Cross-Curvature in Infinite Dimensions. Synthetic definition and spaces of measures.
Wow, that's a mouthful.
I know, right?
Eh.
But trust me, hidden in there is some really cool stuff that applies to things like economics, machine learning.
Oh, really?
Yeah, even matching organ donors.
I would not have guessed that.
It all comes back to this wild math.
It's all about data, really.
Exactly. But before we get ahead of ourselves, let's start simple. Imagine a curved surface, like a bowl that's always right side up. That's sort of what non-negative cross-curvature means. Well, it means no matter how you slice it, the curve always bends in the same direction.
That's a very simplified way to think about it, yeah. But the researchers in this paper are applying this idea to spaces way more abstract than a simple bowl. I mean, think spaces of probability distributions.
Thanks as a, okay, you lost me a little there. Can we bring that back down to earth?
Sure. Imagine all the different combinations of, say, customer preferences for a product, right? You can think of that as a kind of space where each point is a unique set of preferences.
Okay, I'm picturing it.
And the way those points are arranged, how close or far they are from each other.
That's the geometry we're talking about.
Exactly.
Instead of points on a bowl, it's like every possible way someone could feel about a product.
Right.
All laid out in this abstract space. And this math helps us make sense of it all.
You got it.
So it's more than just some theoretical math equation. It has real-world applications.
Oh, absolutely. Think about the kind of complex, high-dimensional data we see everywhere in financial markets, medical research, you name it. This concept helps us understand it.
Okay, now you've really got my attention. But how does knowing about the curvature of these abstract spaces actually play out in the real world?
Yeah.
Do you give me a concrete example? So we're comparing things, different sets of data, stock market trends, all that.
Yeah, instead of just looking at whether stock went up or down.
Right, up or down, that's the basic picture.
This concept helps us understand the geometry of those movements.
The geometry.
Yeah, like how they relate to each other in a more holistic way.
Okay, so it's more than individual data points. It's about the shape of the whole trend in this space we keep talking about.
Exactly, precisely. And to work with these spaces,
Which are already pretty out there, right?
the researchers use something called variational C segments.
Variational C segments. Okay, you're just messing with me now, right?
It does sound a little intimidating.
A little. It sounds like something from Star Trek.
But think of them like specialized measuring tapes.
Measuring tapes for these curved spaces.
Yeah, imagine trying to find the shortest path between 2 points on a hill.
Okay, I'm picturing it.
That path wouldn't be a straight line on a flat map.
Right, it would curve around.
Exactly. These C segments help us find those shortest paths, but in these abstract, curved spaces.
So they're like specialized straight lines for a very specific kind of math problem.
That's a great way to think about it, yeah. And here's where it gets really interesting. They figured out how to define these C segments without using calculus.
And why is that a big deal? Calculus is hard enough as it is.
Because calculus, it can get really, really complicated in infinite dimensions. And this new approach, it kind of opens up a whole new way to solve these problems.
So it's like finding a shortcut through a mountain range.
Instead of climbing every single peak.
Yes,
Yeah.
exactly. And using this shortcut.
They were able to prove some really cool things. For example, they showed that the space of probability distributions
Here we go again with the spaces.
with the 2 Wasserstein distance has non-negative cross-curvature.
Okay, hold on. I need a translator. 2 Wasserstein distance. What in the world is that?
Okay, imagine you have 2 piles of dirt.
Piles of dirt.
Trust me on this one. And you want to move one pile to match the shape of the other.
Okay, I'm picturing it. 2 piles of dirt, different shapes.
The 2 Wasserstein distance is basically a way of measuring the least amount of effort it would take to do that.
So, like, finding the most efficient way to, reshape a pile of dirt.
It sounds strange,
It's a little out there.
but it shows how this math idea applies to real problems.
Okay, I'm starting to see it. The 2 Wasserstein distance helps us find the best way to move or transform things.
Whether it's dirt or data.
Okay, I get it. So by proving that this specific space has non-negative cross-curvature, what are we actually learning? What's the takeaway? So we've gone on this whole journey talking about spaces and distances and curvature. But I'm still waiting for the aha moment. Where does this actually become useful?
And that is the exciting part, you see, because this paper, it connects all of this to better algorithms. Imagine algorithms that are more efficient, more accurate, especially when you're dealing with huge amounts of data.
Give me an example. What kind of algorithm?
Well, one area is optimal transport, which, remember we were talking about piles of dirt?
Yeah, the piles of dirt.
It's like, imagine you need to move products from factories to stores, right? And you want to do it as efficiently as possible so you're minimizing costs.
Okay, makes sense.
Or even think about matching organ donors with recipients.
Oh, wow. Yeah.
Where finding the optimal match is, well, it's literally life-saving.
So are you saying these algorithms, armed with all this mathematical understanding, they can sort through tons of possibilities and actually find the absolute best one?
Exactly. And it's not just, logistics and things like that. This concept is being used in machine learning too. So training AI to recognize patterns like in images and text, all of that really benefits from understanding the geometry of the data.
So you're telling me that things like image recognition, language translation, all these things we use every day, they could become even more accurate and efficient just by applying this mathematical concept.
That's the idea. This paper really highlights how important this is, how understanding non-negative cross-curvature can completely change how we deal with these massive data sets, these complex data sets.
That has huge implications.
Oh, absolutely. Even things like designing auctions, so they're fair, or even voting systems, it all becomes clearer when you're able to analyze their underlying structure in this way.
It's amazing to me how one mathematical concept can have such a ripple effect across so many different fields. Is there one main takeaway from this research that you find the most fascinating?
For me, what's really cool is how they show how this concept, this non-negative cross-curvature, it can be lifted.
Lifted.
Yeah, like you can take it from simple examples and apply it to really, really complicated ones. It's like they're building a bridge between this abstract world of math and the messy real world where we actually need solutions.
So they're saying, here's this specialized tool, and here's how you can use it on the problems you're actually facing.
Yeah, exactly.
That is powerful.
And this paper really feels like just the beginning. I mean, there's so much potential here for future research.
Before we wrap up, any final thoughts? What could be the next big breakthrough in this area?
This research really makes you wonder, what if we could use these insights to design even smarter AI? AI that can deal with uncertainty, make good decisions even when it doesn't have all the information. Imagine systems that are more adaptable, more resilient because they understand the underlying shape, so to speak, of the problem.
Now that's an exciting thought to end on. If you're as fascinated by this world of infinite dimensions and the impact it has on our lives as we are, be sure to check out our show notes. We'll have links to the research paper plus more resources so you can explore these ideas further. And join us next time because we're taking another deep dive into a topic you won't want to miss.
Okay, so get this right. Today we're diving headfirst into, get this, advanced geometry. Yeah, you heard that right. We're talking about something called non-negative cross-curvature, but everyone, and I mean everyone, calls it NNCC. And it sounds kind of intimidating, like something you'd need a PhD for, but trust me, it's way cooler than the name lets on.
Way cooler. It's some seriously cutting-edge stuff. This paper we're looking at, it connects NNCC to things you wouldn't believe. Like, we're talking economics, machine learning, the whole 9 yards.
No kidding. See, I told you. Intriguing, right? And that's why you're here. You're the perfect person to break all this down for us. So the paper, let's get right to it. It's called, get this, Non-Negative Cross-Curvature in Infinite Dimensions, Synthetic Definition and Spaces of Measures. Okay, I gotta admit, even I'm feeling a little lost just reading that title. So where do we even begin?
Well, the thing is, this paper, they take a very, let's say, unique approach. They call it synthetic, which is a fancy way of saying, imagine trying to understand how a car works, right? But instead of looking at the engine and all the parts, you're just observing what it does, how it moves, how it sounds. That's kind of what they're doing here with NNCC. It's a way of understanding this geometric concept by looking at its effects rather than starting with formulas and definitions.
So instead of looking at the blueprint, we're watching the car drive around and trying to figure out how it works from that. I like it. It's like reverse engineering geometry.
Exactly.
That's a really cool concept. But okay, before we get too far ahead of ourselves, let's make sure everyone's on the same page. What exactly is non-negative cross-curvature? Could you give me, I don't know, a simple definition, something even I can understand?
Absolutely. Think of a triangle, right?
Right.
One of the first things we learn in geometry is that all those angles, they always add up to 180 degrees.
Right.
NNCC is like it's a kind of rule. But instead of triangles, it's about the curvature of more complex spaces.
Yeah.
It's how distances between points change as you move through that space. But the non-negative part, that means it avoids any kind of like downward bending or curving.
Okay, I think I'm sort of with you, but can you give me like a real world example, something to help me wrap my head around this whole curvature thing?
Here? Sure. Imagine walking across a field. If it's perfectly flat, distances to other points in the field, they change in a predictable way.
Yeah,
Right.
makes sense.
But now imagine that field is hilly. Suddenly, those distances, they change differently depending on if you're going uphill, downhill, or around a bend. That's the essence of curvature.
Ah, okay, so like NNCC would be like walking on a field, but there are hills, but like no valleys, right?
Yeah, exactly. You got
Yeah.
it. NNCC is all about spaces where that curvature is always non-negative, meaning no sudden dips or downward slopes.
Okay, I think that's starting to make sense, but, and maybe this is a silly question, why should we even care about NNCC? I mean, it still seems pretty abstract, right?
Huh?
What makes this one concept so special that it needs like a whole research paper, let alone us spending time on it?
Well, that's where it gets really cool. And that's where this paper, I think, really shines. You see, NNCC, it's not just some abstract math problem. It's actually surprisingly useful. It's like discovering that the way hills form can also tell us something about, like, I don't know, how traffic patterns emerge in a city, Totally different things, but connected by this underlying principle.
Wait, for real. So you're saying this paper, it suggests NNCC could help us understand things beyond just, theoretical math.
Oh, absolutely.
Okay, now you've got my attention. Give me some examples. How does this actually apply in the real world?
Oh, absolutely. Like take economics, for example. This paper, it shows how NNCC can actually give us insights into how people make decisions, in markets and stuff. Like imagine those decisions are kind of like paths on that hilly field we were talking about.
Yeah.
NNCA could help us predict where people are going to walk, so to speak,
Right.
based on the terrain, so to speak.
So instead of just looking at like, I don't know, numbers on a spreadsheet, we could use NNCC to actually like visualize and predict like market trends and things.
Exactly. You're getting it.
That's wild.
And it gets even cooler, right? Because the paper doesn't stop there. They also connect NNCC to machine learning, which, as you know, that's a big deal these days. And specifically, it's about optimizing algorithms. The ones that deal with comparing like complex data. Think about things like image recognition or what's called natural language processing, all that stuff. Those require comparing like really complicated structures, not just simple data points.
So instead of comparing like apples to apples, we're talking about comparing like entire orchards to each other.
A perfect analogy. And, NNCC, it could give us like totally new tools for making those kinds of complex comparisons, which means potentially, more efficient, more accurate algorithms. And get this, the paper goes even further and connects NNCC to, get this, fluid dynamics. The way like particles move in a fluid, it turns out if we understand the curvature of those movements, that can unlock new ways of analyzing all sorts of complex systems, not just fluids.
Wow. Okay, so we're talking about NNCC popping up everywhere from like the stock market to like the way water flows. That's pretty mind-blowing.
Right.
But this is where the paper like really gets crazy, right? Like it finds NNCC in places you wouldn't expect at all. Like what were some of those like really unexpected examples?
Yeah. So one that really blew my mind was this thing called, are you ready for this? Wasserstein space.
Wasserstein space.
Yeah, Wasserstein space. It sounds like something out of Star Trek.
It really does.
But basically, imagine you're trying to measure the difference between not just 2 points, but 2 different ways of distributing things. Like imagine like resources in a city, right? Or like probabilities in statistics, that kind of thing. Wasserstein space helps us measure those kinds of differences.
So instead of just like the distance between 2 points, we're talking about the distance between like 2 arrangements. It's like, I don't know, measuring the difference between 2 ways of like arranging books on a shelf. Is that kind of close?
Exactly. You got it. And, people have been studying Wasserstein space for a while. But this paper, they show that it also has this like surprising NNCC property, which, that could be huge. It could open up all these new ways of analyzing complex systems, especially ones that involve like probability and distribution.
Wow. Okay, my brain is officially like a little fried, but in a good way.
It's pretty mind-bending stuff.
It really is. And there's another example, right? Even more abstract, something about a space of spaces.
Oh, yeah, this one's really out there. So the space of spaces, it's basically like Imagine if you could compare all the possible shapes and sizes of, well, anything, like every object ever. It's like we're going meta with geometry, you know? We're studying the relationships between shapes themselves.
Okay, yeah, I'm definitely getting a little lost here, but I think I get the gist. It's like we're not just looking at shapes, we're looking at the space that all possible shapes exist in.
Exactly.
Wow. Okay, and that they're saying space of spaces, it also has this NNCC thing going
I've
on.
got it. It's like this curvature concept that goes deeper than anyone thought. It might even, and this is where it gets really wild, it might even connect to quantum
Wait,
mechanics.
seriously, quantum mechanics, like the stuff of like subatomic particles and like the fabric of reality.
I know, right? It seems like a huge leap, but the paper suggests that even the way we describe quantum states, like the very building blocks of, well, everything, could be influenced by NNCC.
So we're talking about the possibility that this abstract math concept, it might be like woven into the fabric of reality itself. That's a pretty profound thought.
It is. And you know what? These are still early findings, but the paper argues that because NNCC is so stable, like under all these different conditions, we're probably going to find it even more places as we keep looking. It's like we've stumbled onto this like hidden pattern in the universe, a pattern that could totally change how we understand, well, everything.
It's like we found a secret code underlying everything.
Yeah.
From, like you said, the stock market to the quantum realm. This NNCC thing, it's feeling less like, you know, abstract math and more like some kind of universal key, you know, unlocking all these deeper truths about how things work.
That's a great way to put it. And that's really what makes this paper and this whole conversation so important. It's not just about, you know, complex equations or whatever. It's about the real world ways that NNCC could change how we understand the world around us.
Okay, I'm fully on board now. So for our listeners out there who are thinking, this is all super cool, but what does it mean for me? What's the takeaway? Where do we go from here? So for our listeners out there who are thinking, this is all super cool, but what does it mean for me? What's the takeaway? Where do we go from here?
It's like we've said, NNCC might be one of those hidden patterns that pops up in all these places we don't expect. Like it could help us understand economics and machine learning, even physics in ways we never thought of before.
Exactly. It's not just theoretical, it's got real world implications. So, like, think about it, right? You're out there, you're working on some problem, and you're stuck.
What if NNCC could give you that new perspective, that breakthrough you need?
Exactly. And that's what's so exciting about this paper. It's like it's opening up all these new possibilities. So, yeah, if you're listening to this and you're working with complex systems, data analysis, whatever it is,
Don't just dismiss NNCC as some abstract math concept. It might just hold the key to unlocking something amazing.
absolutely. And on that note, I think we've given everyone a lot to chew on today. It's been quite a journey.
It really has. This
Yeah.
NNCC thing, it's a real rabbit hole.
It is. But hey, that's what these deep dives are all about, right? Exploring those rabbit holes and seeing where they lead us. So, to everyone listening, thank you for joining us on this wild ride. And until next time, keep those brains engaged and keep asking those big questions because who knows what other hidden patterns are out there just waiting to be discovered.
Hey there. Ready to dive into some seriously cool math with me today? We're going to be unpacking this idea of non-negative cross-curvature.
Yeah, it sounds kind of intimidating, I know. This paper you sent, non-negative cross-curvature in infinite dimensions, synthetic definition and spaces of measures, it's a mouthful.
For real. But the applications of this stuff could be wild. Think economics, AI, even wrapping our heads around like the structure of reality itself.
Exactly, and that's what makes it so fascinating.
Okay, so like level with me, what is cross-curvature in the first place? I'm picturing, I don't know, a bagel, something with a lot of curves.
Okay, so think of it like this. Imagine any curved surface sphere, for example. Cross-curvature is basically measuring how much that surface is bending at a particular point.
Right, okay, I'm sort of with you, but then there's the non-negative part. What's that all about?
Good question. It's like adding a rule that smooths things out a bit. Imagine you're trying to find the shortest path between 2 points, right?
Like on a map.
Exactly. In a space with non-negative cross-curvature, you're not going to suddenly hit a massive detour that adds a ton of extra distance. The cost of the journey changes predictably.
So it's like a map where the terrain isn't completely bonkers. Gotcha.
Exactly. Now, to really get this paper, we need to think about cost spaces and cost functions. Picture bunch of different cities.
Okay.
And you're trying to find the absolute cheapest way to get from one to the other, whether that's based on distance, time, price, whatever matters
Right,
most.
so the cost space is like all the possible combos of cities and ways to travel between them.
Exactly. And the cost function is the math formula that tells you the cost for each combo starting point, destination, plug it in, get the cost.
Okay, now I see how this is all coming together. But I'm still wondering, why does any of this matter? Why are these cost-minimizing paths so important?
Because they're literally everywhere. Think logistics companies trying to move stuff around as efficiently as possible,
Makes sense.
or finance investors looking for the most profitable way to use their money. These are all about finding the shortest path through some pretty complex cost spaces.
So non-negative cross-curvature is basically telling us that these paths, these best routes, behave themselves even when things get super complicated.
You got it. It's a kind of mathematical guarantee that things won't go totally haywire, even with tons of variables and messy multidimensional stuff.
This is already making my brain hurt a little in a good way. But before we jump into the deep end with infinite dimensions, maybe we should give our listeners a moment to process all of this.
Sounds like a plan. This is where things start to get really wild.
All right, so we've got a grip on non-negative cross-curvature, at least when we're talking about maps and cities and stuff.
Right.
But this research paper you sent, it takes us to infinite dimensions.
Mm.
Honestly, that makes my brain go to like that scene in Interstellar with the Tesseract.
Yeah, it's definitely a big jump. Think about it this way. We're used to 3 dimensions, right? Up, down, left, right, forward, back.
Right.
Now imagine a space with countless other ways to move around, each one representing some different factor or variable.
Countless ways to move. So it's not just that the space itself is infinite, but the ways you can travel through it.
You got it. A classic example is something called a Hilbert space. It's like a souped-up version of the 3D world we know. Still well-behaved mathematically, but with infinite dimensions, each one holding a different piece of information.
Okay, so we've got these Hilbert spaces, infinite ways to go. Does non-negative cross-curvature still apply? Can you still find the shortest path with all these possibilities?
That's the crazy thing it does. NNCC still keeps things kind of smooth, even in those insanely complex spaces. It makes sure that moving from one point to another, the cost changes predictably, even with all those dimensions.
So no matter how many dimensions we're in, NNCC stops things from going completely nuts.
Exactly. And this is where it gets really cool for actual applications, right? Because a lot of the problems we're trying to solve at logistics, financial models, understanding data, it's all about navigating these really high-dimensional spaces.
High-dimensional like those Hilbert spaces.
Exactly. And that brings us to Wasserstein spaces. This is a big part of this research paper. Imagine a space where each point, instead of a location, is actually a whole probability distribution.
Whoa, okay. A probability distribution. You're going to have to explain that one.
Sure. Think about something like maybe election polling. You've got all these different polls, each predicting what percentage of the vote each candidate might get, right?
Right.
Each poll is basically a snapshot of a possible outcome, a probability distribution over those candidates.
So instead of points on a map, it's points representing different things that could happen.
Exactly. And a Wasserstein space lets us measure the distance between those distributions so we can compare different possible outcomes.
Okay, so now I see the connection back to cost space. We're not talking about how much it costs to go between cities anymore, but the cost of like moving between different possible scenarios.
You got it. And non-negative cross-curvature is essential for making sense of the geometry of those Wasserstein spaces. It ensures that moving from one distribution to another, the cost behaves in a way we can actually understand mathematically.
So even though it's all these abstract spaces of probabilities, NNCC provides like an anchor.
Exactly. And that's why this research is so exciting. It suggests NNCC could be the key to totally new solutions fields that are all about probability and statistics.
Like artificial intelligence. I've heard that this kind of math is the backbone of a lot of those machine learning algorithms.
That's right. Understanding the geometry of data is crucial for designing good machine learning algorithms. And Wasserstein spaces, they're perfect for representing those complex data distributions, so they're becoming really important in AI.
So this non-negative cross-curvature, which sounded so abstract, it might actually be what makes machines smarter.
It's a powerful tool for sure, and this research suggests it could have even more applications that we haven't even thought of yet.
My mind is officially blown. And something tells me you are not done yet. Okay, my brain is like officially fried at this point.
Yeah.
We've covered so much ground, Koss spaces, Hilbert spaces, even Wasserstein spaces.
It's a lot to wrap your head around, but that's what's so cool about research like this. It's pushing the limits of what we know.
And this whole time we've been talking about non-negative cross-curvature, how it helps us find these shortest paths in all these crazy scenarios. But where does it actually lead us? What's the point of knowing all of this?
That's the real question, right? And the exciting part is we're still figuring out the answers. Take economics, for example.
Okay.
NNCC, it could lead to much better models of how markets actually work, how prices change, even how to design better auctions.
So we're not just talking about some abstract math problem. This has real-world implications.
Oh, absolutely. And then there's machine learning, AI. NNCC could completely change how we understand and use data.
How so?
Imagine algorithms that can go through massive amounts of information, finding hidden patterns, making predictions that are even more accurate than what we have now.
That sounds incredibly powerful. Almost a little scary, to be honest.
I get that. With any powerful tool, there's always the question of how it's used, right?
Yeah.
It's up to us to make sure it's used ethically and responsibly.
True, true. So are there limitations to NNCC? Are there some things it just can't do?
Of course, no single mathematical idea is perfect, right? One of the big challenges is that NNCC, it depends on certain assumptions about these spaces we're talking about.
Right.
And in the real world, data can be messy. It doesn't always fit neatly into those assumptions.
So bridging that gap between the math and reality, that's still a work in progress.
Exactly. And that's part of what makes this research so intriguing. It's not just about getting answers. It's about asking the right questions, pushing our understanding further.
Well, you've definitely given us a lot to think about today. As we wrap up our deep dive into non-negative cross-curvature, any final thoughts for our listeners? Something to leave them pondering.
Don't underestimate the power of ideas, even if they seem abstract at first. Something that starts as pure theory, like in that research paper, it could end up changing the world. Stay curious, keep asking questions. You never know what you might discover.
Great advice. A huge thank you to our expert for guiding us through the fascinating world of non-negative cross-curvature.
My pleasure.
And listeners, we hope you've enjoyed this deep dive. Until next time, keep exploring, keep learning. Hey there, ready to dive into some seriously cool math with me today?
Always a mouthful, that one.
You can say that again.
Yeah.
But honestly, even I was surprised by how this research paper takes a concept that sounds like pure abstraction and makes it relevant to things like, well, everything.
It is remarkable, isn't it?
So no more needing to be a math whiz to appreciate this stuff.
This paper, Non-Negative Cross-Curvature in Infinite Dimensions, Synthetic Definition and Spaces of Measures, really tries to bridge that gap between complex math and real-world applications.
I'm all in. Let's start with the basics, though. I get that NNCC is all about curvature, but could you give me a refresher on how that's usually defined? I remember something about an MTW tensor from my college days, but it's all a bit fuzzy now.
Sure. Imagine for a second that instead of diving into a podcast, you're trekking across a hilly landscape. The MTW tensor is essentially a tool that lets us measure the curviness of your path at any given point.
Okay, I'm picturing it.
Yeah.
But this paper is all about redefining that curviness in a way that's way more flexible, right?
It helps us quantify those ups, downs, and bends using, well, math, precisely. You see, the traditional way of using the MTW tensor to define NNCC has some limitations. It usually requires smooth, predictable surfaces, think perfectly rounded hills.
So we need a new way to think about curvature, something that can handle the messiness of reality.
And unfortunately, the real world rarely cooperates with that level of perfection.
Exactly. That's where this paper's concept of a synthetic definition of NNCC comes in. Instead of relying on complex calculus and those ideally smooth surfaces, they're looking for patterns in how distances behave.
So instead of measuring the curve of a hill directly, we're looking at, say, how long it takes to walk between different points on that hill. That almost sounds simpler.
In a way, it is. It's like finding a shortcut to understanding something complex. And what's fascinating is that this new approach opens up a whole world of possibilities for applying NNCC to problems that traditional methods couldn't even touch.
Okay, now that we understand the limitations of the traditional approach, let's dive into how this paper revolutionizes NNCC. Starting with this whole synthetic definition, what does that even mean in this context? Well, instead of rigid formulas and smooth spaces, We're stepping into the world of cost spaces.
Cost spaces. Okay, you're going to have to break that one down for me.
Basically, a cost space is any set where you can measure the cost of moving between any 2 points. And that cost could represent any kind of effort, distance, time, even money.
So like the cost of getting from my couch to the fridge could be measured in steps, minutes, or even how much willpower it took to resist the leftover pizza along the way.
And within these cost bases, they introduced these special paths called variational C-segments.
Those sound awfully technical. Are we about to get lost in a mathematical jungle here?
Think of variational C-segments as the most efficient routes between 2 points in our cost space, kind of like finding the shortest route on the map, but instead of just distance, we're factoring in that chosen cost.
Okay, I think I'm following. So we've got our cost spaces and these most efficient routes. But how do we actually use those to determine if a space has this non-negative cross-curvature? What are we looking for?
It all comes down to a pretty elegant inequality that the paper naturally calls the NNCC inequality.
Hit me with it. How does this inequality reveal the secrets of NNCC?
Imagine you have 3 points in your cost space and you connect them with one of our most efficient routes, a variational C-segment. The NNCC inequality essentially says that the cost of going directly from the middle point to any other point must be below the chord.
Below the chord. Okay, now you're speaking my language. Can you elaborate on that a bit?
Picture a string stretched tight between the 2 endpoints of your variational C-segment. The NNCC inequality states that the cost of traveling directly from the middle point to any other point on the segment must be less than or equal to the height of that string at that particular point.
Wait, so instead of complex formulas, we're essentially looking for this visual pattern of below the chord to understand curvature. That's surprisingly intuitive.
It is, isn't it? And the real beauty of this approach is that it can be applied to all sorts of spaces, even ones that traditional methods using the MTW tensor wouldn't be able to handle.
This is huge. It means we can now apply the power of NNCC to messy real-world problems that traditional geometry couldn't handle, right? So how does this new definition actually play out when we move beyond theoretical spaces?
That, my friend, is where things get really interesting.
All right, you've got me hooked. Give me those real-world applications. How is NNCC making a difference?
Well, one area where this new definition really shines is in something called optimal transport.
Okay, I've heard that term thrown around. What is optimal transport in a nutshell?
Imagine you're trying to move a pile of sand from one location to another, but you want to do it using the least amount of effort.
So it's like logistics on a whole new level.
You could say that. It's about strategically moving resources, whether that's actual goods, data, or even something like probabilities. And what's amazing is that this new perspective on NNCC helps us understand the geometry of these spaces where this optimal movement is happening.
Okay, help me wrap my head around this. What does it even mean to talk about the geometry of something like probabilities?
That's where those spaces of measures we mentioned earlier come into play. Think of them as maps, but instead of physical locations, each point represents a different probability distribution. And using the synthetic NNCC, we can analyze how spread out these distributions are, which has huge implications.
Huge implications for what exactly? Give me an example.
Let's take something like matching suppliers with customers. Each supplier has a certain capacity. Each customer has a certain demand.
Okay.
Using optimal transport in this space of measures, we can figure out the most efficient way to meet everyone's needs.
So less wasted resources, happier customers. I can get behind that. What else?
And what's even cooler is that the paper gives specific examples of how this new NNCC definition applies to spaces used in quantum mechanics, like Beers-Wasserstein geometry.
Okay, quantum mechanics. Now you're just showing off.
Yeah.
But seriously, what's the connection there?
Well, without getting too deep into the weeds, quantum states, the way we describe those tiny particles, can be thought of as points in certain mathematical spaces. And this new definition of NNCC might give us new tools to study how these quantum states evolve and interact.
So NNCC, from optimizing delivery routes to unraveling the mysteries of the quantum world. Are you seeing a theme here, listeners?
Indeed, and that's just the tip of the iceberg. The paper goes on to explore how NNCC plays a crucial role in a field called mechanism design, which is all about
Designing systems that incentivize specific behaviors, right? I took a fascinating course on game theory back in college. I'm guessing that ties into this somehow.
Absolutely. Think of things like auctions, voting systems, or even how we structure contracts. These are all mechanisms designed to elicit certain
So
outcomes.
are you saying NNCC can help us predict how people will behave in these systems?
In a way, yes. NNCC can provide a new lens for understanding strategic decision-making in complex environments. It could even help us design more robust and fair systems.
That's incredible to think that this abstract mathematical concept could have such tangible impacts on our everyday lives.
It is quite remarkable. And there's even more. NNCC also has the potential to revolutionize how we understand and analyze something called gradient flows.
Gradient flows. Okay, now I'm officially lost.
Imagine a drop of water flowing down a hill. The path it takes is determined by the shape of that hill, right?
Okay, makes sense.
Gradient flows are kind of similar. They describe how things change or flow over time, guided by some underlying landscape of possibilities. And what's fascinating is that this new definition of NNCC gives us a fresh perspective on studying these flows in spaces with infinite dimensions.
Infinite dimensions. You've lost me again. What does that even mean in a practical sense?
Think about something like predicting the weather. You've got countless variables interacting in incredibly complex ways: temperature, humidity, wind speed, and so on. That's an example of a system with essentially infinite dimensions.
Okay, I'm starting to get the picture. So NNCC can help us make sense of these incredibly complex dynamic systems.
Precisely, and not just weather patterns. We're talking about anything from the behavior of financial markets to the evolution of language itself. These are all systems with huge numbers of interacting components.
So it seems like this new definition of NNCC has opened up a Pandora's box of possibilities for applying this concept to a mind-boggling range of fields.
Yeah.
But before we get too carried away, I'm curious, are there any potential downsides or limitations to this new approach that the paper discusses?
That's a great question, and one that I'm sure researchers are already exploring. While the paper doesn't delve deeply into potential drawbacks, it's worth remembering that this synthetic definition is still relatively new.
So, like any groundbreaking discovery, it comes with its own set of unknowns and challenges to unravel.
Absolutely. But that's part of what makes this field so exciting. There's still so much we don't know, so much potential for new discoveries. And that brings us to a thought-provoking question that the paper itself raises.
Okay, I'm on the edge of my seat here. What's this thought-provoking question the paper leaves us with?
The paper focuses specifically on NNCC, but it makes you wonder, are there other areas of mathematics where we could use a similar synthetic approach? Could we find new ways to define and apply other complex concepts, making them more relevant to the real world?
Now that you mention it, it does feel like this paper has cracked open a door to a whole new way of thinking about math. Like, what if we could take some of those notoriously dense theoretical concepts and find those below the chord patterns to unlock their hidden potential? That's pretty mind-blowing.
It really is, and it underscores the beauty of this kind of research.
Yeah.
It's not just about solving equations in isolation, it's about building these bridges between abstract mathematics and the world we experience every single day.
Exactly. We've gone from grappling with the intricacies of NNCC to seeing its potential impact on fields like economics, logistics, even quantum mechanics. It's like this one concept is a key that unlocks deeper insights into how systems behave and interact, regardless of whether we're talking about atoms or, well, Amazon deliveries.
It's a great reminder that math isn't just about numbers on a page, it's a language that helps us decipher the patterns and principles underlying reality itself.
Well said. And who knows what other mathematical mysteries are out there just waiting for their synthetic breakthrough. Maybe one of our listeners will be the one to find it. That's all the time we have for today's deep dive into the fascinating world of NNCC. Until next time, keep those brains buzzing, and we'll catch you on the flip side.
All right, so get ready to dive into the world of non-negative cross-curvature with us today. NNCC, for short. You sent us a fascinating research paper called Non-Negative Cross-Curvature in Infinite Dimensions, Synthetic Definition and Spaces of Measures, and we're going to try to unpack it and figure out what NNCC is and why it matters.
Yeah, it's a mouthful, isn't it? that title.
It is.
But yeah, you're in the right place. This is your crash course on NNCC. We'll unpack the cool examples. We'll even touch on how it pops up in fields like economics and machine learning.
Okay, so I'll be honest. When I first saw NNCC, I thought maybe it was like some obscure government agency or something.
Right.
But it turns out it's all about understanding the geometry of spaces in a whole new light.
Exactly, yeah. Imagine like trying to measure distances, but on a curved surface.
Okay.
Like the Earth.
Okay.
It's not as simple as just like taking a ruler to a map.
Right.
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 So NNCC helps us understand those distances and those relationships.
Yeah.
But on these more complex surfaces, and even in dimensions that we can't even visualize.
Okay, so it's like we're trying to navigate on a sphere instead of on a flat piece of paper.
Yeah, exactly.
But we're not just looking at like maps. We're talking about like probability distributions and algorithms and stuff.
You got it. And the paper actually introduces a really clever way to define NNCC that makes it applicable to these really complex scenarios. They use something called the MTW tensor, which I know sounds a little intimidating.
Yeah.
But it's really just a way to quantify how much a space is curving.
Okay, so instead of just saying a space is curved, this tensor gives us a way to actually measure that curvature.
Exactly, yeah.
Yeah.
And NNCC comes into play because it essentially tells us that this curvature never dips inward in a certain way. It's kind of like it's like saying the space can't have any weird folds or creases that would mess up our measurements.
Okay.
Yeah.
That makes sense, but I'm still trying to wrap my head around how this connects to things like, say, economics.
Yeah.
We're talking about these abstract spaces.
Right.
We're not talking about stock markets.
Right. But think about it this way. Economics often involves understanding how people make choices.
Right.
But within a system of constraints.
Right.
Right. And those choices, those constraints can actually be represented as a kind of space.
Interesting. So you're saying we can use NNCC to analyze things like markets or auctions by understanding the shape of these economic spaces.
Exactly. Yeah. Let's say you're designing an auction.
Okay.
And you want to make sure that it's fair to both the buyers and the sellers. NNCC can actually help you analyze those potential outcomes and make sure that the rules of the auction promote fairness.
Wow, so this is way cooler than I thought it was going to be. So we're not just talking about abstract geometry here. We're talking about designing better systems in the real world.
Exactly. Yeah. And it goes beyond economics too. Remember those complex spaces we were talking about?
Yeah.
Well, machine learning algorithms often have to navigate those spaces to find patterns in data.
Right, like teaching an algorithm to tell the difference between a picture of a cat and a picture of a dog.
Yeah, exactly. And all those images, they exist in kind of a space too. And so NNCC helps ensure that these algorithms are exploring that space in the most efficient way possible, which can lead to better, faster learning.
So NNCC is giving these algorithms a map and compass to navigate these complex data landscapes?
Yeah, it really is. And speaking of maps and landscapes, one of the most intuitive examples the paper uses to illustrate NNCC is the surface of a sphere.
Okay, so now we're back to our trusty basketball analogy.
In a way, yeah. You see, the surface of a sphere naturally exhibits NNCC. Think about planning a flight route from one city to another.
Okay.
The shortest path isn't a straight line on a map. It's that curved path along the Earth's surface, right?
Right, those curved lines you see on those little screens in airplanes.
Exactly, and NNCC helps us understand why those curved paths are actually the shortest distances on a curved surface.
Okay, so even something as seemingly simple as a sphere can exhibit this really interesting property.
Yeah.
But I'm guessing the examples in the paper go way beyond spheres, right?
Oh, absolutely. This is where it gets really exciting. Remember how we were talking about machine learning algorithms navigating through spaces of data?
Yeah.
Well, even the very concept of probability can be represented as a kind of space.
Hold on. You're saying we can think of probability itself as having a shape.
You got it.
Okay.
And just like with our sphere, we can talk about distances and curvature within this probability space.
Okay.
And guess what?
What?
Certain important distances within this space, like the Wasserstein distance, which we'll probably unpack a little bit later, also exhibit NNCC.
Okay, my mind is officially a little bit bent. So we're talking about the probability of something happening, like the chance of flipping heads on a coin.
Yeah.
As having a location in this probability space.
Exactly, yeah. It's a way to visualize and analyze probabilities in a geometric way.
Okay.
And the paper shows how NNCC plays a crucial role in understanding how these probability distributions relate to each other, which has big implications for things like machine learning.
This is blowing my mind. So we've gone from rubber bands on basketballs to the very nature of probability.
Right.
And it all ties back to this concept of NNCC.
Exactly. And And we're just getting started. This paper goes even deeper, exploring how NNCC can be lifted from a simpler space, like our sphere, to a much more complex one, like the space of probability distributions on that sphere.
Lifted. What does that even mean? Like, we're taking the NNCC properties of the sphere and applying them to this more complex space.
You're catching on quickly. That's exactly what it means. And this lifting principle, it opens up incredible possibilities for applying NNCC in new and unexpected domains.
Yeah.
It's like discovering a hidden language that connects different areas of mathematics.
Wow, okay. I am intrigued. But before we journey any further into these mathematical landscapes, let's take a quick pause to process. We'll come back and we'll delve deeper into the paper's specific contributions and how they're changing the game for NNCC research, so we can lift NNCC from simpler spaces to more complex ones. Like taking that NNCC from a sphere and applying it to the realm of probabilities on that sphere.
Right.
That's wild. It's like we're finding these secret passageways between different mathematical universes.
It's a great way to put it, yeah. And this paper doesn't just stop at highlighting those existing connections. It actually introduces a new way of defining NNCC, which makes it even more powerful and versatile.
Okay, so I'm intrigued. What's so special about this new definition?
Well, you see, a lot of traditional geometry, it relies on things being nice and smooth,
Okay.
like, our trusty sphere.
Yeah.
But the real world, it's often messy and unpredictable.
Tell me about it.
Right. And so this new definition of NNCC actually uses these things called variational C segments, which I know might sound a little intimidating.
Yeah.
But they're actually a really clever way to deal with spaces that aren't so smooth and well-behaved.
Okay, I'm going to need you to elaborate on that. Variational C what now?
Variational C segments. So imagine you're trying to find like the shortest path between 2 points.
Okay.
But instead of just distance, you also have to consider like some kind of cost. So for example, maybe certain paths are like more expensive or more time-consuming to travel than others.
Oh, okay. So like choosing between the scenic route and the toll road.
Exactly, yeah.
Yeah.
They might both get you there, but the cost is different.
Right.
And so variational C segments are like those paths that minimize this cost.
Okay.
And they take into account all those like bumps and detours along the way. And the C, by the way, stands for cost, so that makes it a little bit easier to remember.
Oh, I like it. Okay, so it's like we're finding the most efficient routes through these complex spaces, even when they're not as straightforward as our sphere.
Exactly, yeah. And what's really remarkable is that this new definition of NNCC using these variational C segments, it doesn't rely on all those like traditional assumptions of smoothness. It can handle much more like complex, irregular spaces.
So it's like they've given us a new set of tools to explore parts of the mathematical world that were previously inaccessible.
Exactly.
Okay.
And to kind of like really demonstrate the power of these new tools, the paper goes into a bunch of like really fascinating examples.
Hit me with your favorite, like what really stood out to you?
Well, remember how we were talking about spaces of probability distributions?
Yes. Those spaces where like the chance of flipping heads or tails has its own little address.
Exactly. Well, there's this particular distance that's used in probability theory called the Wasserstein distance. And it essentially measures like how different two probability distributions are from each other.
Okay, so if we have one probability distribution that's like a pile of sand, that's really neatly shaped like a pyramid, and then another one that's, more of a sandcastle disaster.
Yeah.
The Wasserstein distance would tell us how much work it would take to reshape one pile into the other.
That's a fantastic way to think about it, yeah.
Okay.
And what the paper shows is that under certain conditions, this Wasserstein space, this space where these probability distributions live, actually exhibits NNCC.
No way. So even though I can't really picture this probability space in my head, we can still analyze its shape and apply all those insights about curvature and C segments to understand how probabilities actually behave.
Exactly. And it gets even wilder. Remember how we were talking about lifting NNCC from simpler spaces?
Yeah, like taking that NNCC blueprint from our sphere and applying it to these more complex structures.
Well, they actually apply that same principle here.
Huh.
They show that if you start with a sphere that exhibits NNCC, you can actually lift that property to the Wasserstein space of probability distributions on that sphere.
Whoa, that's some next level mathematical magic right there. So we're not just analyzing probability, we're connecting it to the geometry of the underlying space itself.
Precisely. And this has huge implications for fields like machine learning and statistics. It gives us a really powerful new way to understand how algorithms might learn from data and make predictions about uncertain events.
This is truly mind-blowing stuff. But before I get completely lost in the mathematical weeds here, can you give me a concrete example of why this matters? Like, why should I care about NNCC and Wasserstein space?
Sure. Imagine you're training a machine learning algorithm
Okay.
to distinguish between different types of images, let's say cats and dogs.
Okay.
Right. You could think of each image as like a point in this very complex image space.
Okay, so I'm picturing like a giant warehouse filled with cat and dog pictures,
Exactly.
each one with its own little coordinate.
Exactly. And now, by understanding the NNCC properties of this image space, we can start to develop algorithms that navigate that space more efficiently,
Yeah.
which leads to like faster learning and more accurate classifications.
So NNCC is like a secret weapon for making machine learning algorithms smarter and more efficient.
That's a great way to put it. And the applications, they go beyond just image recognition. This understanding of NNCC and spaces of probability distributions, it's relevant to anything that involves uncertainty, from predicting stock market fluctuations to modeling, like the spread of diseases.
Okay, this is officially beyond anything I could have imagined. We've gone from rubber bands on basketballs to the very fabric of probability and machine learning, all thanks to this one concept.
And we're not done yet. The paper goes on to explore even more examples of where NNCC pops up, including some really interesting cases related to the world of positive definite matrices.
Positive definite what now? I have to admit that one sounds a bit intimidating, even for me.
I hear you. Trust me, it's not as scary as it sounds. You see, positive definite matrices, these are these really useful mathematical objects that pop up all the time in fields like statistics and machine learning.
Okay.
They're often used to represent like relationships between different variables, like how the price of one stock might be related to the price of another stock.
Interesting. So they're like mathematical tools for understanding, like correlation or connection.
You got it. You know, the paper explores a specific distance used to compare these matrices, called the Beers-Wasserstein distance. And guess what? It turns out that under certain conditions, this distance also exhibits NNCC.
No way. So even when we're dealing with these more abstract mathematical objects, this NNCC property still pops up.
It's amazing, isn't it? It's like we're uncovering this hidden language of geometry that just like permeates so many different areas of math. And this discovery, it just opens up all sorts of possibilities for applying NNCC to new and like really exciting problems.
I'm starting to think NNCC is less like a language and more like a universal law of mathematics. It's everywhere we look.
You might be onto something there. And, you know, this paper, it does an incredible job of not just like identifying these connections, but like rigorously proving them using this new framework of variational C segments.
So they're not just saying, hey, look, we found an NCC over here. They're showing us the mathematical proof that it's actually there.
Exactly. It's rigorous, it's groundbreaking work, and it's paving the way for like a whole new wave of research in this area.
This is all incredibly fascinating, but I have to admit, my brain is starting to feel a bit full. Let's take another quick pause to absorb all this incredible information, and then when we return, we'll wrap things up by exploring the broader implications of this research and what it means for the future of NNCC. All right, so we're back. We've talked about spheres, we've talked about these like super abstract probability spaces, but I feel like we need to address the elephant in the room. Okay. The complexities of some of these equations.
Right.
Because as elegant as all of this sounds, I have a feeling it's not always easy to actually work with NNCC in practice. The paper mentions something called the MTW condition. Is that related to these challenges?
It definitely is related. So the MTW condition, it's kind of like a cousin to NNCC, but maybe a little bit more relaxed in its requirements.
Okay, so if NNCC is like the straight A student of the geometry world, MTW is maybe a little more laid back.
That's a great way to put it. Yeah, in more technical terms, NNCC demands that the curvature measure, which we've talked about, this MTW tensor, is non-negative everywhere in every direction.
Okay.
Whereas the MTW condition, it only requires it to be non-negative in certain like specific directions.
So it's a bit more forgiving.
Right.
A bit less strict.
Yeah.
But I'm guessing there's kind of a trade-off there, right?
There is. One of the key insights from the paper is that while NNCC behaves really well when we lift it to more complex spaces, as we've discussed,
right,
the MTW condition doesn't always follow those same rules.
So it's like trying to build a house.
Yeah.
NNCC gives you this really strong foundation that you can like confidently build upon, but MTW might result in a structure that's a little shakier, a little less reliable.
Exactly. And the paper gives a really concrete example of this with the Wasserstein space,
Okay.
that space of probability distributions we were talking about.
Right, where each probability distribution is like a unique arrangement of sand in our giant warehouse.
Exactly. They show that even if the underlying space, let's say like the floor of that warehouse, satisfies the MTW condition, the Wasserstein space that's like built on top of it might not. It's like the good behavior doesn't always transfer over.
That's really interesting. So it's not enough to just check the MTW condition in a simple space.
Yeah.
If we want to work with these more complex structures that are built on top of it, we really need NNCC.
You'd hit the nail on the head. And this seemingly subtle point, it has big implications for researchers working in this area, because it tells us that if you're dealing with things like probability distributions or other complex spaces, focusing on NNCC just provides you with a much more solid footing.
Yeah, if you want a really robust theory, you need a strong foundation. But why do you think the authors of this paper, why did they choose to highlight this distinction between NNCC and MTW? It seems like a very nuanced point.
It is nuanced, but it's really insightful because, remember, this paper is all about expanding the frontiers of where NNCC can be applied. And so by showing that the MTW condition can be a bit finicky in certain situations, they're essentially highlighting like the robustness and the versatility of their new NNCC framework.
It's like they're saying, look, our new tools can handle even these really tricky situations where other approaches might fall short.
Exactly. And it's not just about showing off or anything. Like, understanding these limitations, it's crucial for like guiding future research, right?
Mm-hmm.
It's about knowing when you need like the really heavy duty equipment versus when a simpler tool will suffice.
Right, like choosing the right map for your journey.
Exactly.
If you're just exploring a well-charted city, you can probably get away with a very simple tourist map. But if you're venturing off into uncharted territory, you're going to need something a lot more detailed, a lot more reliable.
I love that analogy. That's great. And so, this paper, it provides that detail, that reliable map for anyone who's venturing into the world of, NNCC research.
So where does this all go from here? What's next for NNCC? What are the big unanswered questions? What are the exciting avenues for future exploration that this paper kind of hints at?
Well, the authors themselves are the first to admit that we're really just scratching the surface of NNCC.
Okay.
There's a whole universe of potential applications out there waiting to be explored.
Like what? Give me an example. What other fields could benefit from, like an NNCC makeover?
Well, they specifically mentioned areas like fluid dynamics,
Okay.
where understanding curvature and flow is absolutely crucial. Imagine being able to apply these NNCC tools to model things like ocean currents or even like air patterns with even greater precision.
Wow. So it's like we could use NNCC to map out these invisible forces that are shaping our planet. What else?
Another area they touched on was network analysis.
Oh.
So imagine applying NNCC to understand that complex web of connections in things like social networks or biological networks,
Okay.
or even the internet itself.
So instead of just seeing this jumble of nodes and links, we could use NNCC to understand the underlying geometry of these networks.
Exactly, yeah. It's about seeing the world through this NNCC lens
That's fascinating.
and, uncovering the hidden structures and the connections that really govern these complex systems.
This has been incredible. We went from the very concrete world of spheres and distances to this really abstract realm of probability distributions and beyond. It really does feel like we're just starting to unlock the secrets of NNCC.
And that's what makes this research so exciting, right? It's not just about, providing answers. It's about asking these new questions, pushing the boundaries of what we thought was even possible.
To our listeners out there, keep exploring, keep asking questions, and who knows? Maybe you'll be the one to make the next big breakthrough in the world of NNCC.
Yeah, until next time.